In this session, we will start by the keynote from Dongmei Zhang. So please allow me to introduce Dongmei. Dr. Dongmei Zhang is the Assistant Managing Director of Microsoft Research Asia, where she leads the research area of data intelligence, knowledge computing, information visualization, and software engineering. Dongmei founded the software analytics group in Microsoft Research Asia in 2009. Since then, she has developed many software analytics tools that created high business impact. So in recent years, Dongmei and her team have also developed many products on business intelligence and cloud intelligence. Dongmei has her PhD from CMU. So without further ado, I will pass the time to Dongmei. So Dongmei, you could start anytime now.
Thanks, Hongyu. First, let me just share my slides. Can you see it?
Yeah, we can see it. Good.
Okay, perfect. All right, thank you very much, Hongyu. Good afternoon, good morning, good evening, everyone. First, I'd like to thank Hongyu and the conference organizing committee for giving me this opportunity to share with the ICSME community our research work and our experiences on tech transfer to make impact in practice. I really wish that I could be with all of you, all of us could get together for this great conference. It's just that I hope that everyone is doing well during this unprecedented time. Okay. So before I started, let me use a couple minutes to introduce our lab and our research group. So I work in Microsoft Research Asia, aka MSRA. MSRA is in Beijing, China. The building on the left you're seeing in the picture is our office building. MSRA was founded in 1998. In June this year, MSRA opened a new lab in Shanghai. So not sure how many of you have already known this. So you can see like two buildings on the left-hand side of the picture. So our Shanghai lab is located on the 43rd floor of the tower on the right. So I hope that when COVID-19 is gone and when our lives go back to normal, of course the new normal, you could visit us in Beijing and also in Shanghai. MSRA is Microsoft's largest research institute outside of the United States. It primarily focuses on computer science research, and it also pays a lot of attention to transferring technologies to Microsoft products, just because we are an industry research lab. In addition, we also do incubation, trying to explore the next big thing. One thing MSRA is proud of is a huge number of talents it helps cultivate over the years. We have got more than 7,000 alumni, including 6,000 interns who are all over the world studying and working in different universities, institutions, and companies. There are 6 research areas in MSRA: natural user interface, intelligent multimedia, artificial intelligence, cloud and edge computing, big data and knowledge mining, and computer science fundamentals. As Hongyu introduced, I'm responsible for the big data and knowledge mining area, which is an interdisciplinary area. Our work also touches cloud and edge computing and natural user interface. So our group is called Data, Knowledge, Intelligence, DKI in short. We have 3 research themes around data: understanding, generation, and interaction. Understanding is straightforward. Generation is also important because in the era of data, people do not only consume data, they also generate a huge amount of data anywhere and any time, including social media contents, productivity documents, And for developers, writing code, test cases, and documents, as well as fighting bugs, is all about data generation. With a breakthrough in AI, there are more natural and easy ways for people to interact with data. For example, using natural language and speech. Along with graphical user interface, the multimodality interaction greatly enriches users' experiences. So those are the three main themes of our research. As you can see on this slide, within our DKI group, we have three research groups, and software analytics, like big data mining, and also knowledge computing. Those are three research groups. Among the three groups, software analytics is the biggest one, and it has the longest history. So today, I will first look at our early work on software analytics, and then I will talk about how we shifted our research focus onto cloud intelligence. I will use a couple of projects as examples to introduce the research landscape of cloud intelligence. At the end of the talk, I will also share some of our experiences working on cloud intelligence and my thoughts on some future research opportunities. So first, let's look at software analytics in the early days for us. As Hongyu introduced, I founded the software analysis group in MSRA in 2009. We had 12 people on the team back then, as you can see from the picture. And very luckily, we have, like most of us are still working together today. So indeed, it has been a very long journey. So there are like two major stages in our research on software analytics. The first one is from like 2009 to roughly like 2014, 2015 timeframe. And then the second one is from 2015 to now. When defining software analytics at the beginning of our research, we emphasize a few important points. The first one is the data-driven approach. That's like a given, right? And then the second one is about the research topics, including quality of software systems, user experience, and development productivity. Here, it should be noted that the runtime behaviors of software systems and the user experience are as important as source code and the common development tasks. The third point we wanted to emphasize is about the requirements on the output of software analytics. Specifically, the output, we think, should be insightful and actionable. It should not be regarded as good to know or like fine to forget or ignore after you just show that to people. So software analytics is an interdisciplinary area cutting across computer systems, machine learning, data mining, and information visualization, as we're seeing on the right-hand side of this diagram. So our team members have diverse background in these areas, and we have benefited a lot from this over the years. Here, I should say a special thank you to Professor Tao Xie at Peking University. So our collaboration started in 2010 during the very early days of software analytics. Together, we defined software analytics, and we promoted that in the software engineering community. So like till today, we're still collaborating. So very grateful to have such a great collaborator. In addition to publishing papers, we also worked very hard towards getting some of the research results into real use, because we truly believe that software analytics is naturally tied with software development practice. The data we study in our research come from real systems. The problems are the pain points of the practitioners. The users or the target audience of our research are the practitioners. And we build tools that work for the practitioners to use to solve their real problems in production. With a great partnership and also support from product teams, we got opportunities to work on problems involving data from a wide range of software products, as you can see from here. including operating system, developer tools, large-scale web services such as search and Office, and cloud computing platform. Along with our product team partners, we made some impact in practice. For example, when the security team in Microsoft, back then it was called Microsoft Security Response Center, MSRC. When they found one vulnerability, they would use our code clone search system to find similar instances of the vulnerable code across the shipped products in the company. Another example is that built on top of our cost stack mining work, we built a tool called StackMine to help developers effectively and efficiently analyze millions of cost stacks. The performance analysts in Windows use our tool in their performance investigation, which often involve huge number of cost stacks. StackMine helped boost their productivity. So here I'm listing out some major data sources we used in our research in the early stage and the different topics we studied. Now looking back, there are a couple of notable observations. So one is that we started with different topics around source code, which is very common in the software engineering community. And we quickly added more topics from the software system side, including logging, for example. Although logging deals with source code, it's not written for understanding the source code. It is written for understanding the runtime behavior of the software system and debugging the software system when problems occur. The other observation, which may not be very clear from here, is that the systems and the study range from traditional operating systems, like operating system like Windows, to software services like Office 365. Around 2010, on-premise software products started to migrate to the cloud, making it possible and easy to collect large-scale runtime data reflecting system performance. This observation actually paved the way to the second stage of our software analytics research, cloud intelligence. So now let's take a moment and look at what was happening in the software industry in the past 10 to 15 years. One significant paradigm shift was the emergence of cloud computing. In 2006, Amazon released Elastic Computing Cloud, EC2. In the next 5 to 6 years, quite a few big software companies like Google, Microsoft, IBM, and Oracle already released their own cloud computing platforms. Microsoft Azure came out in February 2011. Since then, businesses in different industries started to realize the benefits for them to migrate into the cloud. And more importantly, the opportunities it brought up to transform their businesses. Specifically, the value of data to businesses has been widely accepted. Businesses need to collect huge amount of data, store the data, process the data, get insights from the data, and then use the insights to take actions, either to improve their existing business as well, or create new business opportunities. And also, they need to do all of the above at scale and with low cost and agility. They can't afford to use the traditional IT approach to do this, especially for small to medium businesses. Therefore, cloud computing would be a natural choice for them. So the implication of this is profound. It means that cloud computing platform would become part of the basic infrastructure of our society. The non-functional properties of software systems would become immensely important for cloud computing platforms, such as availability, reliability, performance, security, etc. Some practitioners would go as far as saying, reliability is a feature, performance is a feature. They're not exaggerating. It is very true that end users would not have patience on slow websites, and enterprises would not bet the success of their own customers on unreliable platforms. As researchers in an industry lab, we definitely experienced the impact of the trend of cloud computing. On one hand, Azure is one of Microsoft's big bets. There's still a lot of room for improvement for the platform to improve today, let alone 5 years ago. On the other hand, cloud computing and the digital transformation it enabled got us to think about digital transformation and the software industry itself. On the surface, the question may seem a little bit odd, since software is naturally digital. But deep down, the question is really about how we develop software, operate software system, and engage with customers. We should think about how frequently we're still making decisions based on experience and instinct. In how many systems we're still flying dark. How many times we don't discover problems in our system until customers complain about them, etc. With this thinking, we realize that software analytics is the digital transformation of the software industry itself. Given the trend for businesses to migrate to the cloud and embrace digital transformation, it will be a great opportunity for conducting research and making impact if we focus our software analytics research on cloud computing. We call this new topic cloud intelligence. In addition, something else big happened in the past 10 years. DNN got a big breakthrough at ImageNet Challenge in 2012. Since then, there has been a re-emergence of AI research and applications until now. So you know how hot it is. So deep learning also opens new opportunities for us in the cloud intelligence research. So now let's make cloud intelligence a little bit more formal. Cloud intelligence is to use AI or ML, machine learning technologies, to effectively and efficiently build and operate complex cloud services at scale. I hope this diagram looks familiar to you. It has like 3 topics: services, engineering, and customers. To embed AI in there, the 3 topics are AI for system, AI for DevOps, and AI for customer support. Here, I'd like to emphasize on the high expectation on cloud intelligence. With cloud intelligence, the services are expected to have built-in intelligence, meaning they should be able to monitor themselves, analyze and assess their status, and have the ability to self-adjust. Of course, there will be developers and operators in the loop when needed. With such intelligence, when dealing with service issues, the services will be proactive instead of reactive in order to minimize customer impact. Working with our colleagues in Microsoft Research and our partners in product teams, we have been promoting the research and practice of cloud intelligence, both inside and outside Microsoft. In February this year, we had we have the first cloud intelligence workshop at AAAI, which got a lot of interest, and it was very well attended. If we look at the steering committee members here, we can see quite a few familiar names. So we have members, representatives from both academia and industry, and we have representatives from both system and software and engineering communities. We hope to work with more people in both academia and industry on cloud intelligence. In recent years, AI ops has become a very popular word. It was first coined by Gartner in 2017. According to Gartner, AI ops is the application of machine learning and data science to IT operation problems. Compared to cloud intelligence, Gartner's AI ops concept focuses only on DevOps, whereas cloud intelligence has a much broader scope, including AI for system and AI for customer support. Recently, there is also effort trying to broaden the concept of AI ops to include the system and customer aspects. For example, 一农党 Qin Weilin and Peng Huang presented a technical briefing at ICSME last year on the real world challenges and research innovations of AIOps. So now let's look at the problem space of cloud intelligence. For services, the problems around service health include the following: how to measure service health that spans multiple aspects, including availability, reliability, performance, security, etc. Like using metrics of components and resources, how to detect anomalous behaviors that may lead to service health problems. Furthermore, can we predict whether some service problem may happen after a period of time so that we can take proactive actions? When a problem happens or about to happen, can we recommend recovery actions, or can we let the system do auto-healing when appropriate? For engineering, all the problems are familiar ones listed here. I'd like to talk a little bit about auto triage, which is also called incident triage. Incidents are the unplanned service interruptions or service outages in the cloud platform world. They are inevitable in online systems. When an incident is detected by engineers or service monitors, an incident report is created in the incident management system. Then the incident report needs to be automatically assigned to the responsible team for investigation, which is called incident triage. Here, you may ask, can we apply the traditional bug triage techniques? Yes and no. Bugs and incidents have many things in common, but they also have different characteristics. Like bugs are often reported and treated individually in the triage context. Incident reports are different. There may be many incident reports that are correlated and have the same root cause. The reason is that online service systems are highly complex. One incident can lead to another incident and many others more. All these incidents are reported by different monitors, resulting in many different but related reports. So how to triage the incidents effectively? And to what extent can the bug triage techniques be leveraged here? So those would be interesting problems to explore. For customers, let's look at intelligent customer support. To cut down the cost and improve efficiency, how can we enable self-service for customers? Also, how can we provide actionable suggestions to customers? When a customer does talk to a service support personnel, how can we help make the communication easier? As we are seeing here, the problem space of cloud intelligence is quite broad. The list here covers quite some topics, but we may find more topics when we go deep into the space. On this slide, let's use a different perspective to look at the problem space of cloud intelligence. We extract 4 major scenarios from the problems: prompt detection, problem localization and diagnosis, prediction, and optimization. Each scenario has its own challenges. For example, for problem detection, we often need to deal with a lot of data problems, such as the noise to signal ratio is very high. There are missing data, and more severe challenge would be quite often there are very few labeled data. On the left-hand side, I'm listing some of our work in the past few years, trying to tackle some of the challenges in cloud intelligence. Next, I will use a couple of example projects to show in more detail on what we have done. The first project is disk error prediction in cloud computing platform. As we know, availability is a critical issue for cloud computing platforms. All the cloud platform vendors have been trying to improve the availability of their platforms. Availability is often measured by unplanned virtual machine downtime. When the downtime is less than 26 seconds per month, the availability is set to reach 5 nines. So you can see how high a bar we have set in there. Among the various issues that cause VM to go down, hardware issues are one of the top reasons. Our partners in Microsoft Azure did further investigation and found that this problem is the most severe one among hardware issues. A typical cloud system like Azure usually has like hundreds of millions of hard disks. This related problem has become one of the most significant factors contributing to the service downtime. In addition to Microsoft, the importance of this problem is also observed by researchers in other companies, such as like Facebook and Google. They reported in their paper about like 20 to 57% of disks experienced at least one sector error in datasets collected over a period of 4 to 6 years. So in order to reduce VM downtime, it is not enough to replace disks after they fail because VM is already unavailable then. We must take actions before disk fails in order to avoid bringing down the VM, which requires us to do prediction. Now, let's look at what kind of actions can be taken if disk failures can be predicted. The actions also reveal the use scenarios of our prediction model. There are two actions. One is VM allocation, which means that when certain type and certain number of VMs are requested, Azure Compute needs to find the appropriate hosts for these VMs. If we can predict the health status of disks, then the hosts with healthy or healthier disks can be selected to host the VMs. The hosts with unhealthy or faulty disks would be avoided. This way, proactive actions can be taken at the VM allocation time to reduce the possibility of VM going down in the future. The other action is called live migration. It is a technique to move VMs from one host to another without disconnecting the client or application. Obviously, live migration has advantages. Since there's no VM going down, the impact on the hosted client or application is minimized. But there's still some impact depending on the situation of the host. For example, there is seconds of blackout time, and there may be a period of time the performance of the hosted client or application is impacted. In addition, running live migration, the action itself consumes capacity resources. So all of these just imply that there's a cost associated with live migration. So we should still be very cautious about making the decision to do live migration or not. So you may ask, why should we care about the actions? I will share the reasons in a minute. Okay, so now let's look at how the existing approaches solve the problem. Obviously, we were not the first ones to work on this problem. So for the existing approaches, their problem definition is to use the smart data. Here, SMART stands for self-monitoring, analysis, and reporting technology. So their problem definition is to use the smart data of disks to predict whether a disk would completely fail after a certain amount of time. Please note that it says completely fail, okay? So among the existing works, there are mainly 3 approaches to solve this problem, as we are seeing here: statistical approach, unsupervised approach, and supervised classification. Although they reported good results in the publications, when we tried these approaches on the real data from production, none of them worked very well, unfortunately. So when we talked to our partners in Azure and understood the use scenarios of the model, we also studied the problem again and got a couple of observations. The first one is that, in general, like disks exhibit errors before they completely fail. Based on our statistics, we found that disk errors, on average, occurs almost or about like 60 days, 16 days earlier than complete disk failure. Furthermore, these errors can cause virtual machines to go down or reboot. This means that predicting complete disk failure may be too late to be helpful in terms of reducing VM downtime. What we should do is to predict disk errors, which would provide some lead time for taking actions. Then the next question is whether there are any data recording disk errors. The answer is yes. These errors, such as latency errors, timeout, and sector errors, are often reflected by the system-level signals, such as OS events, recording symptoms such as file operation errors, VM not responding to communication requests, etc. So given this observation, we introduce system-level signals as another data source in the prediction problem. We also changed the prediction target from predicting complete failure of disk to predicting disk errors. The second observation is to recognize the pitfall of using cross-validation in disk error prediction. In cross-validation, the dataset is randomly divided into training and testing sets, and the temporal dimension is ignored. Therefore, it is possible that the training set contains part of the future data and testing set contains part of the data in the past. This approach does not work when it comes to online prediction, which is the scenario of disk error prediction. Online prediction uses historical data to train a model and predict future. So there must not be any time overlap between the training dataset and the testing dataset. Similar data leakage issues were also pointed out by researchers in the software engineering area in the past. In the case of disk error prediction, the characteristics of the cloud environment itself also requires us to strictly separate the training dataset and the testing dataset using the respecting the temporal direction, the temporal dimension. So specifically, there are some time-sensitive features, meaning these features have temporal nature, and their values vary drastically over time. Some features may be easily affected by environmental changes to the cloud system. For example, the disks on the same rack or the same motherboard may experience similar attribute changes caused by unstable voltage. However, such changes may not happen before the time of prediction. If we use cross-validation, then we may utilize the knowledge from the future, which is incorrect. So to emphasize the point again, in the case of disk error prediction, we must do strict online prediction. We just cannot use the cross-validation not respecting the temporal dimension. And then we also have the third observation, which is also important. So the third observation is that the dataset is extremely imbalanced. The ratio of faulty disks and healthy disks is about 3 to 10,000. In this case, if we formulate the problem as a supervised classification problem, then the model would lead to high accuracy, but very low recall. So what can we do? We could try some sampling approaches to improve the recall, but at the same time, the previous, the precision could be sacrificed, which is not acceptable in our case. So now let's recall the use scenarios we talked about earlier, VM allocation and live migration. For VM allocation, it does not necessarily require a yes or no answer on the health status of a disk. In fact, if a ranked list of disks based on the health status is provided, it will be quite helpful to the system because the ranking helps the system find healthier disks to use and avoid less healthy ones. This means that we can formulate the problem into a ranking problem instead of a classification problem. The issue of imbalanced data will be mitigated when we learn a ranking model. In addition, to leverage live migration to reduce the potential VM downtime caused by disk errors, we can try to determine the top end unhealthy disks by taking into account the cost of live migration. I'll skip the details here, and you can find that in the paper. So the key takeaway here is that understanding the use scenario is super important because it may directly impact how we formulate the problem. To wrap up this one, our solution was deployed in production in Azure, and it has been running for about 2 years. According to the evaluation of our Azure partners, our solution successfully saved around 63,000 minutes of VM downtime per month. Okay, the second example is intelligent virtual machine pre-provisioning, PPS in short. Let me first introduce the background of virtual machine VM pre-provisioning. VM provisioning is a system management process that creates a new virtual machine on the physical host server and allocates computing resources to support the VM. These computing resources typically include CPU, memory, and quite often it involves storage as well. Provisioning is the most common and essential operation in Azure. Its performance, meaning how fast it is, directly impacts users' experiences. There's no doubt that if a cloud computing platform does not do a good job on VM provisioning, then very likely it will lose customers. Therefore, the provisioning performance is one of the top metrics in Azure. To accelerate VM provisioning, a common practice is to get a pool of resources and pre-provision some VMs. This way, when a VM creation request comes in, if there is a match in the pre-provisioned VM pool, then this VM can be directly used to complete the rest of the provisioning process. Otherwise, the new VM has to be provisioned from scratch, resulting in longer provisioning time. As shown in the PPS process, the pre-provisioning algorithm plays a critical role because it decides how many VMs should be pre-provisioned for each VM type. After getting the context, now let's look closely at the VM pre-provisioning problem. There are 2 knowns and 2 unknowns here. The size of the resource pool is known, which poses a constraint on the pre-provisioning. The historical demands for each VM type are known. For the unknowns, one is that we do not know what the demand will be in the future for each VM type, and we need to predict that. The other unknown is how to fit the future demands into the resource pool. Since there may be many different ways to do it, we should target at getting an optimal solution, well, as optimal as possible. So now let's look at the problem formulation. Given n time series as input, representing the demand of a VM type from T0 to Tn-1, the output of the algorithm is the number of VMs to be pre-provisioned at time t for each VM type. We formulate the problem as a prediction and optimization problem, with the objective function to maximize the pre-provisioning hit rate and minimize the over-provision rate. Here, the hit rate means that the percentage of the incoming VM provisioning requests filled up by the pre-provisioned VMs. Obviously, we want to maximize this metric. Over-provision rate means the percentage of pre-provisioned VMs that are not used. It is important to minimize this rate to achieve high efficiency on resource utilization. When we solve the problem, we should take into account the set of constraints on CPU, memory, storage, and network bandwidth, etc., into consideration. So, of course, there are challenges. Actually, quite a few challenges in this problem. So first, there are a huge number of VMs I think in the thousands in terms of scale, and their demand patterns are very different. So this makes the demand prediction extremely hard. Second, prediction introduces uncertainty, which impacts the final result through optimization. How should this effect be taken into consideration so that we can achieve better result? That's the second challenge. And then the last one is about the NP hard problem. Essentially, the optimization is done in the discrete domain. So the problem is NP hard. Here is the our work. So we proposed a uncertainty-aware framework for prediction and optimization to solve the problem. There are three components in this framework. In the prediction component, we use ensemble learning to address the challenge of predicting demands for huge number of VM types with different demand patterns. Please note that here we have a framework, and for this prediction component, it's a placeholder. It can be replaced by other prediction methods. Okay. And then the second component is the optimization component. So here it takes as input the output of the prediction component, including both the predicted results and the prediction uncertainty. We model the prediction uncertainty using GMM. This part is important. Also, this is a difference between our work and the previous work, which I will talk about later. Also, as the third component, we have a hyperparameter like selection component. So what do we need to have here? Because there are some hyperparameters in the entire modeling process. For example, in the prediction component, some prediction models have their own internal parameters, and in the optimization component, since it uses a two-mode search, heuristic search algorithm to find the optimization solution, it also has a probability parameter to control the heuristic search. So to achieve the best result, we designed this hyperparameter selection component in order to tune the hyperparameters. The key ideas here is to using the Bayesian optimization. And we have a surrogate model to relate the hyperparameters to the modeling performance. And then we use the model, the surrogate model, to iteratively select the best set of hyperparameters. So I talked a little bit about the existing work just now. So if we look at the existing work, there are mainly two representative approaches. So one approach is to use a two-stage approach, which is completely separates the prediction part and the optimization part. Compared to our framework, only the prediction results are passed to the optimization component, and the uncertainty of prediction is ignored. Also, there's no feedback loop from the optimization all the way back to prediction. So only, the training only happens around prediction. So in this case, it cannot address the second challenge we talked about earlier. Another representative approach, which would be a no-brainer these days, is to put everything together and train a deep learning model. But before this can be done, some relaxation needs to be added to make the optimization problem a continuous optimization problem. This means that the optimization problem solved by deep learning is not the original one. It is an approximate of the original one. This is fine to do, but it may not be the best way to address the third challenge we talked about earlier. We compared our approach to the existing work, both the two-stage approach and the deep learning approach, and our approach outperformed both of them. In addition, we also worked closely with our partners in Azure, and we deployed this algorithm in production. It has been serving the VM pre-provisioning need at a massive scale. According to the evaluation in production, the hit rate of our algorithm is around about like 93%, and over provision rate is reasonable and stable. In addition, the median of the VM provisioning time is reduced by about like 42%, indicating that our algorithm actually brings real benefit in real world applications. So we're pretty happy about that one. So next, I'd like to share some of our experiences working on software analytics and cloud intelligence. More recently, our experiences working working with especially with the Azure. So like during this experience sharing, I will also talk about some research opportunities moving together. So I'm just putting the two topics together. So my first learning is about the system aspect of software engineering. In the software engineering community, we do extensive research and build many tools to help developers write code to achieve the design functionality, to help them write code with good practices, to stay away from bad smells, and to help them write code fast by auto-completion, not only at line level, but also at the snippet level. We help them design unit tests, we help them debug their code, give them methodologies and tools to better maintain their code, etc. So all of these are of tremendous value. Source code is written to run. When running software systems or dynamic systems, they may suffer from functional problems and non-functional problems too. Borrowing the two concepts from the control theory, I would ask, as a developer, I may ask, is my system observable and controllable at any time? This means that, do I know the status of my system at any time, or do I just fly in the dark? Can I make adjustment to the system as needed at any time? Or it is on its own, and the only way for me to control is to shut it down. So the non-functional problems can become very difficult to debug and fix when the system becomes more and more complex. This challenge is manifested even more in building cloud services, especially at the infrastructure layer. So how can we help developers become more aware of the runtime behaviors of their systems? How can we help them come up with better designs and write a better code to address the non-functional properties of the system? How can we help them make their systems more observable and controllable? Hard-coded configuration parameters are very common in source code, and developers may keep putting more in their code. With the system mindset of being dynamic and adaptable, can those static values be replaced by machine learning models to achieve better performance? How to get over, if we want to do this, how to get over the cold start problem? How can we make machine learning models explainable so that developers can trust them and use them? How to mitigate when the machine learning model fails? If we have a machine learning model as part of our system, how shall we maintain and evolve such systems? I think those are all like questions for us to think about. So along with this thinking, I also see some like research opportunities. So the first one is about instrumentation. How can we get data about the system we build? In practice, like quite often instrumentation still comes as second thought. Like because developers are busy implementing features, and they may not have enough bandwidth to think through the design of instrumentation and get it done. Like nowadays, there are many logging libraries and tools available for developers to use. But the more difficult questions may still be where to log, How can we enforce instrumentation as first-class citizen as the code that implements features? How can we reduce the cost of instrumentation? How can we ensure the quality of the telemetry data? When the code changes, can we automatically suggest the changes to the corresponding instrumentation? Like earlier during the talk, I talked about software analytics being the digital transformation of software industry itself. To make that happen, at the first step, we need to help developers get quality data about their code, their system. The second opportunity is around prediction-based design. This is the part of AI for system many people talk about today, but it has a unique perspective. Traditionally, developers are very good at designing reactive actions or components when getting certain signals. This means that something is happening right now, and I'm going to do X. But prediction-based design opens up new possibilities. Basically, just imagine there is a crystal ball telling developers some information about the future. For example, what the workload looks like in the next hour, what the capacity status of a cluster looks like next week, or in the disk error prediction case, what the disk health of the disk would look like in the next, say, 3 days, etc. With the information about the future, developers can design proactive actions or components, which was not possible in the past. Quickly, I will just use one example to further explain this. So I will use the buffer management in computing clusters in the cloud platform. The capacity of a cluster is allocated to host VMs according to user requests. In general, some buffer capacity is reserved to accommodate for tenant growth, software update, or to heal the failures, etc. Then there comes the question, how much buffer should be reserved? If it is too much, then it is a waste of capacity. If it is too little, then we run the risk of failures down the road. So if we can predict the status of the workload in the cluster, and if we can predict the capacity status of the cluster, then this prediction will be very useful in terms of adjusting the buffer size dynamically. So the third opportunity is around prediction and optimization. So here I'm bringing back our uncertainty-aware framework for solving this problem. It is a general framework that can be used in different scenarios in software systems. For example, how to allocate virtual machines in a cluster to achieve high capacity efficiency, given a group of servers, how to place different services on those servers to avoid hotspots, and how to do workload packing, how to allocate and rebalance power, etc. Obviously, our uncertain-aware framework is just one solution, and it still needs to be improved. It would be great to see more researchers work on this problem and come up with new techniques. So the second thought I want to share is about technology transfer or making impact in practice. Like throughout the years, there have been many successful examples of making practice impact in the software engineering community. However, until today, tech transfer still feels like a very difficult thing to do. Being a researcher in an industry lab and being a researcher on software engineering, I feel the responsibility to learn and to practice tech transfer as part of what I do. So this is why when we started software analytics research more than 10 years ago, we made tech transfer an important mission for ourselves. So I think I will share a few learnings around tech transfer. So the first one is about finding critical scenario. As researchers, we make hammers, right? Like big hammers, and we want to find nails and hit them right on the head. But there may be too many nails to hit. Like some are big and some are small. It takes effort to understand the real needs and the pain points of practitioners in order to find the big nails, i.e. the critical scenarios. I will use our code clone detection work as an example. We first did research on code clone detection, and we built a tool to detect near code clones in a given code base. we put a lot of thoughts into building the tool in order to make it easy for developers to use. For example, we do not require the code to be compiled first before using our tool. Like developers only need to give us a pointer to their code repo, and it will work. We also build an end-to-end system with easy to use GUI interface to make it easy for developers to consume the detection results. We got some engagement from product teams using our tool. We got some results, we got some feedback. However, those engagements were more like trials without long-term commitment of using the tool as part of their development process. Later on, through our engagement with the security team, I mentioned the tech transfer case earlier, we realized that finding security vulnerability due to code clones is a huge value. It's a very important scenario for the security team. Indeed, it was one of their pain points back then. Without an effective tool, after finding a piece of vulnerable code, the security team would contact the product teams with the code and ask them to check and whether there would be similar vulnerable code in their own code bases. With our code clone search tool, which we just built a separate tool based on the core algorithm. The security team could get a list of candidates and send them to the product teams to review and verify. This way, the security team became more constructive and more targeted with their work. So the second learning is about closing the loop. So I'll be short on this one. So which is particularly important for data-driven projects. So earlier, like between 2009 and 2012, during our, we built a tool called SAS, stands for Service Analysis Studio. So it was used to detect like service anomalies and provides diagnosis suggestions. And also it recommended the mitigate suggestions to the developers. We wanted to get developers' feedback in the tool by just clicking a button to tell us whether our recommendation is useful or not. Unfortunately, very few developers gave us feedback in the tool. So that was a hard lesson learned there. Without this feedback, we cannot continuously tune our model, and we cannot drive our research forward. So in the future projects, when we work on, we paid a lot of attention at very early stage to see whether there would be opportunities to close the loop and get the feedback. So I think I will, considering the time, I think I will stop here. And just to summarize, before I do that, I want to show you this slide. There are definitely opportunities around tech transfer as well. I'm listing 3 here. The first one is about how to systematically incorporate domain knowledge into our research or into the models we built. I think that's very important one, also an interesting one around tech transfer. And then the second one is about how to conduct interdisciplinary research to achieve the end-to-end results. So as software engineering researchers, quite often we need to work with other researchers from other areas like system, like programming language, like the machine learning, like information visualization. So how can we do that effectively? And then last but not least, I would invite you to roll up your sleeves and to join us. You're very welcome to contact us to find collaboration opportunities. And also we're hiring. So if you are interested in joining an exciting industry research lab, then you're very welcome to contact us. So to summarize today, those are the key points I have talked about today. The software analytics and the digital transformation of software industry itself. Also, cloud intelligence has become a very important topic in interdisciplinary topic in several communities. And also, how can, for future research opportunities, how can we help developers get the system perspective more effectively? And together, we hope that we can do great research, and we can also have opportunities to make to use the results of our research to make impact in practice. So I'll stop here and to take some questions. Thank you very much, everyone, for your patience.
Yeah, thank you, Dongmei. Yeah, thank you for your comprehensive and insightful talk. So now, because of the time limitation, we only have 1 or 2 quick clarification questions. So perhaps now you could unmute yourself and you could ask. You can also post some questions to the chat box or Slack channel. So yeah, any questions from the audience? Maybe we have 1 or 2 clarification questions. So yes, so there's one question from Clara. Excellent talk. Just wondering, what kind of features do you use to predict the disk failures?
Oh, that's a very good question. So first of all, I would recommend getting our paper. So all the details, the detail about the features are in the paper. So essentially, I talked about like 2 different kinds of data sources. The smart data and also the system level signals we use. So in addition to the raw signal, we also do like intensive like feature engineering to try to get good features out of the raw signals. So please refer to the paper for the details.
Okay, good. So last question. Any question from the audience? So one question is that how do you exclude the noise data? I think it's about the data noise.
Well, I think let's see. So like depending on the different scenarios, right? Different problems we deal with. But in general, the general statistic approaches we use. So that would be those the first one we use to deal with the noise. Yeah. So I think it's so. I'm just wondering, like, do you have like specific like concerns around noise in your question, or?
Yeah. So okay. So maybe after this keynote session, and we could further discuss about these questions. So if you have any questions, then you can always approach Dongmei because of the time limitation. So perhaps we could stop here.